This is the mission 54 organized by Space Analog Station Habitat Marte. And today we have a presentation of Bryan Ho about scaling MOXIE. Okay, Brian, when you want, you can start. Thanks.
My name is Brian. Today, for the next few minutes, I'll be talking about scaling MOXIE. This is Habitat Mart. A few things we're going to look at today. We're going to look at a recap of what MOXIE is and the current limitations of MOXIE. We'll go into the proposal of how we're going to scale it, some considerations, and lastly, we'll talk about some future works related to MOXIE. So just to recap, MOXIE stands for the Mars Oxygen In Situ Resource Utilization, or ISRU experiment. The goals of MOXIE, there's two primary goals, is really to utilize local resources on Mars through in situ resource utilization and be able to produce oxygen from carbon dioxide from the Martian atmosphere, the carbon dioxide being the local resource and oxygen being our desired output. So just to recap a bit more about how the MOXIE works, the current MOXIE has three stages. We have the CO2 acquisition and compression stage, the CAC. We have the solid oxide electrolysis, the SOXC or SOXC, and the monitor and control systems, the MCS. The diagram you see below is a good kind of flow chart to show how the MOXIE actually works. On the left, we start with the CAC, where we intake carbon dioxide through a filter to filter any impurities. With a pump, we can pump it in and compress it. And then we move to the SOXC, where we're actually heated up, and then we facilitate a solid oxide electrolysis via the SOXC. And then lastly, once we create our desired outputs, our oxygen and our other reagents, we have carbon dioxide and carbon monoxide. We can split those, and then with the control system, we can determine how much oxygen we created. And then lastly, we'll filter those out of the system, and the oxygen can be used, the CO2 can be expelled. So looking a bit more to the SOXC, and this is where this proposal will focus on. The SOXC essentially works like a multi-layered system. We have the carbon dioxide going in through a negative electrode. We go through this dense ceramic electrolyte, which then will create the oxygen. So essentially break it down into two oxygen ions. And finally, we will, for the two oxygen ions, to create one oxygen molecule. The equations of the electrolysis are here. Ultimately, we have the input is 2 CO2. The output, we have O2 and carbon monoxide. So the current limitations of the current MOXIE is, number one, the current MOXIE can only produce approximately 6 to 10 grams per hour of oxygen. For propellant production, we're looking at on the magnitude of 1,000 kilograms or more. For human breathable oxygen, we're looking about on average 1 kilogram per day. And so when we need to scale MOXIE, we have to think more about how much we need for the propellant. Human breathable is a negligible value on the grand scheme of things. So what do we need for the actual propellant? What do we need the propellant for actually? So right here is a kind of a quick summary of a Mars mission. So we're looking at a SpaceX, let's say a Dragon rocket, the Dragon rocket. And this entire top part where we launch to Mars, we have the satellites around Earth. We have the system lands on Mars, and we have a lander. All of that will require resources from Earth. Now, once we establish base on Mars and spend some time there, this entire section right here, the Mars ascent, trans-Earth cruise, and the return to Earth, ideally, all the propellant during that time would be able to be generated from local resources on Mars. And so what we're looking at is solely this part of the entire mission, and this would be categorized as the Mars ascent phase. So for a SpaceX Dragon capsule, some values that we looked up is we require approximately 4,250 meters per second to get the vehicle back into Mars orbit. Now this translates approximately to 955 kilograms of propellant that are required to get back to Mars. And if you look at about a 1:3 fuel to oxidizer ratio, we're looking at about 716 kilograms of oxygen needed just to get one capsule back into orbit and then hence back to Earth. Below you have a diagram of just what the MAV, or the Mars Ascent Vehicle, would look like, and we have the Earth Return Vehicle, which is the upper portion of the capsule. The Mars Ascent Vehicle will break off. Essentially, the Mars Ascent Vehicle will break off as we return back to Earth. So a few assumptions that I'm going to make for these calculations, but these are obviously going to be variable depending on the mission. But for the sake of this presentation, approximate mission length on Mars will be 10 months. And so 10 months translate to about 7,300 hours. Now, to create the 716 kilograms of oxygen that we need in 10 months, on average, we'll need to output approximately 98.1 grams per hour of oxygen from our MOXIE system. And this doesn't. This is a bit. This is not conservative. If this does not account for any failure modes or account for inefficiencies. But we'll get into that in a second. To recall, our current MOXIE prototype that's currently on the rovers can only output about 6 to 10 grams per hour of oxygen. 10 grams being much, I guess, very optimistic, and 6 grams being a bit more conservative. And so what we're looking at is that for every cell of MOXIE, we have to determine how many cells of the MOXIE do we need. So the requirements we're looking at, if we need 98.1 grams per hour and we only can do 6 grams to be conservative, approximately we'll need 18 MOXIE cells to facilitate the oxygen production. Now, I guess this is also assuming that all cells are running 24 hours for the duration of the mission without any stop, without any maintenance, without any fail, and also no faults in the system or no system failures and so forth. On the right, this is from one of the papers that I've been citing for this one. We have an example cell of what a MOXIE would look like, as well as the 18 cells stacked on top of each other to facilitate the electrolysis. Obviously, it's rounded up because you can't have 17.5 cells. Now, some considerations to take in for the MOXIE. Now, the size of the actual SOXY cell is actually limited. So the company that manufactures the SOXY cell for the current MOXIE estimates that the max size of a SOXY is approximately 127 centimeters cubed. Now, why is that important? Because this actually drastically influences our power requirements. Instead of having one large cell that's over 1,000, maybe like 2 meters cubed. Depending on the max size of it, this will drastically influence the design, the size, the power, and the efficiency, and so forth. So just going back to the original equations, recall that our equations for producing oxygen in the SOXY for the electrolysis, we take 2 carbon dioxide molecules. We break that down into two carbon monoxide and 2 oxygen ions. And this important step right here, 2 oxygen ions will create 1 oxygen molecule, but also create 4 electrons. And then the third step is carbon dioxide. The third step we can just cancel out, and basically this is the ultimate reaction. But this intermediate step is really important. The reason being is that during this oxygen producing step, 4 electrons are produced. And this is how we can calculate the molar flow rate using this one. So the molar flow rate is calculated, denoted by NO2, and it's moles per second, molar flow rate. It's calculated by taking the current divided by the Faraday's constant, depending on the amount of electrons produced. In this case, it's I/4F. Now, converting molar flow rate to mass flow rate, which is much more usable in our case, for moles to second to grams per hour, we can create the equation to I/3.3503. Substituting some previous established values, at 6 grams per hour of oxygen production, if we put in 6 grams of mass flow rate, along with this denominator of 3.35, the required current that we need solving for I is about 18.7 amps per cell. So over the 127 centimeters cubed of each individual cell, we're looking at about a current density of 0.147 per centimeter. Thanks per centimeter. Sorry, this is centimeters squared, not cubed, per centimeter squared. Now, after establishing the amount of those power calculations, there's one thing to also keep in mind for considerations. Number one, if we supply too much current, we can actually overextend the process, this electrolysis process. And one thing we have to look for is this carbon monoxide. So carbon monoxide in the present state exists as a gas, and this byproduct as a gas can be filtered easily via the monitoring control system. However, if we supply too much power, or sorry, the voltage is too high, what can happen is that we have a inadvertent, I guess, secondary reaction where the carbon monoxide actually splits into carbon and more oxygen. Well, more oxygen is good, right? Yes, but however, the carbon is a very, very negative byproduct. Reason being, carbon exists in solid form in this case. So if this reaction were to occur where we actually go beyond and split the carbon to oxygen, we'll have what you find in traditional automotive engines or airplane engines, where we'll actually have solid carbon that begins to deposit in the system, and this will severely impact the efficiency and could also facilitate system failures to the system. So the takeaway from this is that we have to find a way where we supply sufficient voltage to facilitate the 6 grams per hour, 7 grams per hour of oxygen production, but not so much to the point where we overextend ourselves and start creating carbon deposits in our system. Example here, this is just from it's a intake valve for just an automotive engine. The carbon deposits can be detrimental. Will be detrimental to the system. So looking at one of the papers I looked at, and I'll link that in references, the experiments show that approximately 1.2 volts is the limit to not exceed, and there's a variety of factors that will change that, but for simplicity for this presentation, we're looking at 1.2 volts. So with the current of 18.7 amps and the voltage of 12.5 volts, the power we're looking at per cell is approximately 22.45 watts per cell, and our previous established requirement of 18 cells to produce sufficient oxygen for the 10-month mission, looking at 442 watts total power. So now, just wrapping up at the end, this entire scaling was looking at solely the SOXY and how we can increase the amount of SOXYs and the electrolysis to facilitate the oxygen that we need. But there's some future work to look at. Number one, what happens if we increase the inlet flow rate? What happens if we can intake more carbon dioxide? How do we update the system and adjust the systems that we can accept more carbon dioxide? Now, down the road, right now our limitation is about 127 centimeters squared of each individual cell. What happens if we increase the SOXY cell size? How does that affect our input, output, and power requirements? I guess the bigger question is also, how do we power this system? Not only do we need 404 watts of power, but if we change different variables, we'll also be needing to adjust our power calculations. On top of that, it's also there's a lot of energy loss due to thermal energy as well. How can we use that to our advantage, and how do we also facilitate dissipating the heat? The efficiency of each individual subsystem is worth looking at. We have the CAC, the SOXY, and the MCS. Is there ways we can improve efficiency, output? A lot of the calculations that we talked about earlier, we're assuming no faults, 100% efficiency, and so forth. Now, is that really what happens in practice? It's hard to say at this point, but if looking to the efficiency of subsystems. And lastly, one last thing is more about the variability depending on location that we're looking at. Now, this is something more of a macroscopic level, is if we have the MOXIEs operating at the equator of Mars versus the poles of Mars, the pressure, the temperatures are variable. Even the altitude, if we're on a mountain, how does the pressure, temperature, and the variability affect our output? And so these are all things to look at that will require much more significant research to look at. Now, just some references. The one paper that I looked a lot in was the scaling of the MOXIE for Zonor sample return, as well as some other thing. Another reference, just look at the requirements for oxygen. And that wraps up the presentation. Thank you for listening.